very much, Jeff. So what I would like to do is show you a little bit how we have used the funds that ICTAS has given us in ways that sort of not just helps our own research, but helps developing the BIST area at Virginia Tech in general. And I think if you want to have a fundamental progress in bio-inspired science and technology, you also have to sort of think a little bit what the big picture is and think which are the factors that really make a difference, right? Where is it that biology is better than engineering, right? It's not everywhere better than engineering, but it can do certain things better. So here's the first key concept that nature is good at, and that is diversifying. Right? So let me give you an example about, what is that, 70 years ago, VW came up with the beetle, and then they went on and made 21 million of the beetles, and I don't want to step on the toes of any beetle fan here, but to me they're all more or less the same. And so it happens nature also invented the concept of a beetle just 300 million years earlier, and it went on to make 400,000 different types of beetles, right? Beetles that can swim in the water, aquatic beetles, beetles that live in the desert. And so that's, I think, something we can learn from nature. If we have this one really good concept, but how can we adapt it to so many different uses, right? So to explore this question, we need data, right? We need data on all these different species so that we can crunch around with them, maybe in a computer or in the lab, and see what's happening here, right? What are the principles? What has nature been doing and been up to here? So what we have worked on is we have worked with a partner, the Smithsonian Institution, the National Museum of Natural History, because they are a huge library for biodiversity, right? They have essentially the known part of the world's biodiversity in backrooms in alcohol. And so if you want to do engineering analysis, what you have to do is you have to get it out of the backroom, out of the alcohol, onto your desktop computer, or into your computing cluster, so that you can crunch away and see, so what has been going on here? So we've been working with them. What you see in the center is a concept that we have for making a digitization setup that will allow them to digitize the data. The Smithsonian has sponsored a senior design project that is currently churning out pieces for this setup, so that's something that is underway. We have also worked on how to digitize entire specimens, right? We are only interested in certain parts of an animal if you do engineering, but the Smithsonian wouldn't let us cut up their valuable specimens, right? So we have to work with whole animals, and that's a good thing, right? Because then tomorrow you have some other idea. If you have it all, you can never be caught short. So what you see on top is models of entire animals, and maybe I do have time, can quickly show you the video, right? So we have worked on, and that was done with the ICTAS money. We have worked with the School of Visual Arts to find actually ways how we can visualize entire specimens, how we can process the data. That was done with the ICTAS funding, and then this idea, right, that you can visualize an entire specimen. So that's not a real physical model, it's a CT scan, right? And so you can visualize the entire specimen. If you like, you can take layers off and look inside, right? So first we are looking at the skin, now we are looking at the skeleton, right? And we can get that all this information in one go, and then also take it apart in one go, right? So now you can see the brain of the bat, right? And so these are pretty automated versions, so the idea is to do that hundreds of thousands of times. Okay, so that was this video. Let me quickly go back to the presentation. Yeah, and finally, for engineering, of course, you want function, right? So these balls down there, these are not Christmas from a Christmas tree or something, ornaments, but this is function, this is acoustic function. So we have been working on methods. How can we actually take functional characterization across a lot of specimens, species, and align those? So that's the sort of the one performance secret. And the next one is, if you look at again, technical devices, say you have a megaphone for emitting sound. Well, there's two observations about the megaphone. One is that it is a very simple device, right? Very simple shape, and it is also static. That's also something, and that's good for us, but for an engineer, you can work out how the megaphone works. You can do that analytically on a piece of paper, right? So that's why it's a good thing. Nature doesn't do analytic math. It doesn't care about simplicity. It doesn't care about stationarity, but it cares what's the best solution. Right? And so that's what we have on the right-hand side is what the megaphone of a bat. Right? So you see how much more of a complicated structure it is, and that's already a static complicated structure, but in addition, it has quite a few degrees of motion. And you see here we are exercising all these different degrees of freedom that we have in there. And again, this is work done together with the School of Visual Arts, where they have nice techniques for animations that they use to rig up characters for animated movies, and then so to make the different facial expressions and so on. So we asked them to rig up a bat nose sleeve for us, and that's what we have here. So what comes with this is a slider so that we can control all these degrees of freedom that the bat has. The bat in its nose sleeve has probably more degrees of freedom than you have in your face, or in your entire face, for making gestures. So you imagine how difficult the communication with the bat is. And then we can control those. And so the entire workflow here is that we use our facility in China to get data of what the actual live bats do, that on the top left, and we make these models, rig them up, so that we can do all these motions that the bats go through, plus more, but so we can do artificial things. And we have gotten quite a lot of help from ACS, from the advanced computing systems, right? Because once you exercise all these degrees of freedom, you get lots of shapes, right? So now you really need big iron computing power to analyze them, so that's what we're doing. And then we get functional characterizations on the right. So that's sort of a bit how the specific work that we have been doing with ICTA support feeds into sort of the big picture of bio-inspired science and technology. I think I should really maximize this. I don't see the icon. So with the last slide, what I would like to do is summarize sort of how what BIST at general. I'm summarizing again the services from our research for BIST in the upper right, I think upper left. I don't think I go through that. But then I've tried to collect a little bit where BIST stands at Virginia Tech as a whole. So I've asked researchers in the area to send me their grants and send me their papers. So the tally is that there's about 18 grants that people have told me about that are currently in effect. And then they account for $21.9 million. You see the funding agency is a bit heavy on the NSF. The Smithsonian has given us a little bit money for a senior design project. Not the amount is not significant, but it's nice to sort of having convinced them that they should actually invest in research at Virginia Tech, and we'll have a meeting with them in May that is sponsored by Don Leo in Arlington to show them what we have done, and hopefully that will then sort of move that process forward. We have, besides that meeting, there's also success that Mike Garvin had, who led us for this BioBuild iGap. So we have now an internal iGap in a bio-inspired area. I think that's also nice to have. Journal publications, I know of 35 journal papers, but I think people were not as diligent in reporting those, so I would definitely think it's way above 40. So it's not conference papers, just journal papers, and in this area, right? So this is not all the papers of the people who do bio-inspired science and technology, but only papers where they actually talk about bio-inspired science and technology. Yeah, so we have this idea of digitizing with the museum. I'm seeking support for that from the Keck Foundation. So this year the university has selected this idea as the one that should go forward to the Keck Foundation. So we have a shot at this. We have, with our partner in Shandong University, want to invest in this relationship, bio-inspired science and technology as well. They are sponsoring a symposium in Shandong this summer. That brings me to the key collaborators. Right? So it is the Smithsonian Institution that is a key partner, and not just the National History Museum. Also, they also have an institution-wide office for digitization that are working with us, and also other museums, American Museum of Natural History, Carnegie Museum, Field Museum. They will all be at this workshop in May, and then of course Shandong University and the industrial design for automation setup that was done by the Shandong University of Art and Design. So that's in a nutshell what I have for the BIST area.